Scientists believe that the building block of the universe is the Big Bang. However, this theory is not sufficient to explain dark matter. Because dark matter is not like ordinary matter, it has a very different structure. First of all, we cannot see it. But the fact that something is not visible does not mean it is not there. Just like we cannot see the gas molecules formed by boiling water. When water boils, these molecules transition from a liquid state to a gaseous state. However, they are so small that they cannot reflect light sufficiently. Therefore, we cannot see them directly with the naked eye. So what is it that we see? How do we see this steam that is released? When the molecules come into contact with cold air, they condense to form water droplets. What we see as steam is actually this droplets. In the first moments of the universe, everything was extremely hot. Of course, much hotter than water. We are talking about a temperature billions of times greater than the core of the sun. This extraordinary heat allowed matter and energy to transform into different forms. Scientists believe that right after the Big Bang, there were regions in the universe filled with intense energy. According to the theory, the energy in these regions also transformed after a while and created dark matter with a silent explosion. I say silent because signals we know, like light and sound, did not emerge during this process. Just like the evaporation process of water, the energy in the universe might have transformed into dark matter under certain physical conditions. Of course, we can detect water molecules with a microscope, but we cannot see dark matter in any way. We can only feel its physical effects. If dark matter didn't exist, galaxies wouldn't be able to hold together in the way we see them today. Stars would have already been flung into space at their current speeds. There is something that holds all of this together. Almost like an invisible glue. Look, we can explain this with numbers as well. The Milky Way galaxy rotates at a speed of 220 km per second. However, calculations with visible matter suggest that this speed should be 160 km per second. This 60 km speed difference cannot be explained without dark matter. So how did this hidden force come about? Before this question, we need to look at the formation of ordinary matter, because at least we have an idea about its formation. The Big Bang. The universe was formed 13.8 billion years ago with a tremendous burst of energy. Immediately after the Big Bang, it expanded at an incredible speed within a time frame much smaller than a trillionth of a second. In the first seconds, there was an unimaginable temperature reaching trillions of degrees. About 10 microseconds after the Big Bang, quarks combined to form protons and neutrons. 3 minutes later, protons and neutrons combined, forming the first atomic nuclei. However, because the universe was too hot, atomic nuclei could not combine with electrons to form atoms. Until 380,000 years later. When the universe cooled sufficiently during this period, nuclei composed of protons and neutrons captured electrons to form the first atoms. As a result, photons or light were released. We can still see that light today. It even has a name: cosmic microwave background radiation. 100 million years after the Big Bang, hydrogen and helium atoms condensed under the influence of gravity to form the first stars and galaxies. But where was dark matter during all of this? Did it also form with the Big Bang like ordinary matter? Or was there another process that created it? Scientists suggest that dark matter formed alongside ordinary matter with the Big Bang. They say that just as ordinary matter formed in that hot environment right after the Big Bang, dark matter particles might have also formed. They say there is no problem with this. They substantiate this idea as follows. Dark matter particles might have interacted with ordinary matter and reached the same temperature. As the universe expanded and cooled, these particles might have lost their interaction with ordinary matter and become invisible. And since that day, we might only be sensing the existence of dark matter through gravitational effects. We are sure that this last sentence is true, because many cosmological observations prove the existence of dark matter. I mentioned the speeds of galaxies to you. The stars within those galaxies should normally be rotating much more slowly. But they are rotating at incredible speeds. Ordinary matter does not provide enough gravitational pull to keep these stars together. An extra force is needed for this. That is dark matter. Another proposed evidence is WIMP. That is, the weakly interacting massive particles hypothesis. This hypothesis is one of the most popular approaches to the formation of dark matter. It is believed that these particles emerged during the high energy density of the early universe. According to the assumption, WIMP particles interact with ordinary matter only very weakly. However, they have a greater mass than ordinary matter particles like protons or neutrons. If we could return to the early periods of the universe right after the Big Bang, we might be able to see WIMP particles with the naked eye. It is thought that these particles might have interacted with matter and remained in equilibrium for a short period. Over time, they might have lost this interaction and become invisible. However, let's not forget that this is a hypothetical type of particle. In other words, we still haven't been able to prove its existence, but some experiments are being conducted to prove it. In fact, I had prepared a video explaining the studies related to quantum detectors. In addition to experiments like LUX-ZEPPELIN and Xenon 1T, some trials are also being conducted at CERN. But so far, no evidence of the existence of WIMPs has been found. All of these are based on a scientific foundation. However, the standard Big Bang theory still cannot explain how dark matter was formed. In other words, there are many missing pieces in the puzzle. The biggest mystery is the nature of dark matter. If it had formed during the Big Bang, we should be able to observe it because it would interact with light. However, we cannot see it. Another issue is the thermal equilibrium and isolation problem. According to the standard theory, dark matter might have reached thermal equilibrium with ordinary matter during the Big Bang. In other words, these two types of matter might have collided with each other, exchanging energy, and eventually reaching the same temperature. You can think of this like a hot cup of tea cooling down to room temperature over time. However, even if this were the case, it still doesn't explain why dark matter stopped interacting with ordinary matter. In addition to all this, the effect of dark matter is another question mark. We're talking about an effect large enough to keep galaxies together, but we don't know the source of that effect. Also, how dark matter constitutes 85% of the total matter in the universe is unknown. So such a powerful force, how and when it became so dominant is a big mystery. Cosmic fluctuations also do not provide sufficient evidence. So even if we observe these, we cannot understand why dark matter behaves so differently from ordinary matter. The standard Big Bang theory can explain ordinary particles like protons, neutrons, and electrons. However, it cannot define which particles dark matter is composed of. You will remember just now, I mentioned weakly interacting massive particles hypothesis. However, these are not a natural result of the Big Bang theory. No evidence has been obtained regarding this so far. All these missing points leave big question marks in our minds, and inevitably lead us to this question: could there have been another process that formed dark matter? For example, another explosion. Two important scientists working in the field of astrophysics, Katherine Freese and Martin Wolfgang Winkler, proposed this theory in 2023, which further confused minds. The term dark Big Bang was used for the first time in this article. So yes, the article suggests that there might have been another Big Bang after the Big Bang. What do you mean? Not one but two Big Bangs. This theory attempts to fill in the missing points of the Big Bang. What was the biggest mystery about dark matter? Its lack of interaction with light, meaning it is invisible. These two scientists argue that such a situation could only occur with another Big Bang. The article suggests that the dark Big Bang could produce gravitational waves. This places the theory within a testable framework. So far, we have not been able to detect these waves. However, scientists believe they can prove this theory with precise measurements in the future. The article also mentions an independent area called the dark sector. The dark sector is an area that does not directly interact with matter and light in the visible universe, but has a series of interactions within itself. According to the theory, a phase transition may have occurred within this area. This could have led to a dark Big Bang. Remember, we gave the example of boiling water. What happened as the heat increased? Liquid water turned into gas molecules that are invisible to the eye. A similar process may have occurred in the formation of dark matter. And at the end of this entire process, gravitational waves may have formed in the fabric of the universe. So have we been able to detect those waves until now? No. Can they be theoretically detected? Yes. However, detecting these waves is almost impossible with current technology. We haven't even been able to detect the cosmic gravitational waves formed after a massive event like the Big Bang yet, because the frequencies of these waves are very low. If a dark Big Bang occurred, detecting the waves it produced is also impossible with today's technology. Detectors like LIGO and Virgo can detect powerful events such as black hole mergers. For example, LIGO detected gravitational waves from two black holes that merged 1.3 billion years ago on September 14, 2015. However, much more sensitive detectors are needed to detect the waves produced by the Big Bang. The first space-based observatory, LISA, developed by the European Space Agency in collaboration with NASA, may have such potential, and it is planned to be launched in 2035. LIGO and Virgo operated on Earth, while LISA will operate in space, thus being completely independent of atmospheric effects. And perhaps one day it might find some traces of the dark Big Bang. Two scientists from Colgate University, Richard Casey and Cosmin Illy, expanded the theory in a paper published in 2023 and presented a new mathematical framework. Casey and Illy suggest that gravitational waves caused by the dark Big Bang can be tested with some experiments. They even go further by explaining this with mathematical data. So, they say that these waves can be detected no matter how low their frequency is. This is the mathematical proof of it. Of course, all of these are just theories for now. But let's not forget, many things discovered in science were once theories. Science progresses in this way. Every new answer brings a new question with it. First, we discovered the light that emerged with the Big Bang. However, over time, we realized that the majority of matter in the universe is invisible. Now, we are trying to understand this invisible side. Without understanding it, we won't be able to grasp the true value of light. This reminds me of human nature. There are aspects within all of us waiting to be discovered, parts that make us who we are. Without understanding our own unknowns, we will never know how bright our light truly is. Inside us, there is much more than what is visible and known. Our true potential, like dark matter, might be hidden in that invisible side of us.